Well, class. Okay, so yeah, I posted this worksheet on Canvas and kind of just go over these problems. And then if there's any questions, we can talk about it back in class. But let's look at problem 1. We have this box that is being lifted at a constant speed. So we have gravity and tension. And it says a 42 kilogram box is being lifted by a rope at a constant speed of 1.5 meters per second. Now we don't actually care how fast it's moving, just that it's a constant speed. And so the acceleration is 0. And let's calculate these forces. So to start out with gravity, we have 42 kilograms times 9.8 meters per second squared. So, sorry, don't know why I put that there. It's 42, not 4.2. So let's say the force of gravity is around 412 newtons. So, 3 significant figures. And because this is moving at a constant speed, tension must also be 412 newtons. So the net force acting on this object is 0, so no acceleration. And so to calculate the work, it's lifted through a distance of 18 meters. Let's do 412 times 18. So we'll have newtons times meters, which is joules. Let's just do this real quick. So the work done by gravity and the work by tension, let's look at tension. Say around 7,400 joules. That'd be the work done by tension. So we know the force, 412, multiply that by the 18 meters, and there we go. Now the work done by gravity is going to be minus 7,400 joules. And there's 2 ways we could see that. One is just directly calculate. We know this force is 412 newtons in magnitude. It is downwards. So we're going to have the same numerical answer. Another way we could look at it, though, is that because it's moving at a constant speed, there's no change in its kinetic energy by the work energy theorem. And so that means that the net work done is 0. And so if tension does positive 7,400, gravity would have to do minus 7,400. Okay, now I'm going to leave most of this up here. Let's look at the next problem. Says, very similar, but now we have that same 42 kilogram box, but it's being lifted by a rope that has tension 540 newtons. So greater than gravity. So we should expect a net upward force of 128 newtons. Okay, so now we're going to start out by what is the work done by gravity, and it's going to be exactly the same as before. When you're calculating the work done by a particular force, it doesn't matter what any of the other forces are doing. And so, we change the tension, that has no effect on the work done by gravity, as long as it's going through the same displacement. So, but when we calculate the work done by tension, now we have to use the force of tension, which is different. So I can do 54 times 18, and then multiply by 10. So 9,720. So that would be the work done by tension in this case. And then the net work, we just add these two. One's negative. So, I'll just write it out. 9720 minus 7400. So the net work is around 2320 joules. So again, net work, you just add the work done by all the forces. And so that number is going to be the change in kinetic energy. And since that's a positive number, this object is going to speed up, which is exactly what we would expect to happen because there's a net upward force. And so we know the magnitude of the kinetic energy. Let's calculate the change in kinetic energy. Now in this case, we're assuming that the box started from rest. So the change in kinetic energy, that would just be its final kinetic energy. That's equal to the net work being done. And so the kinetic energy, we can solve for the velocity. So let's do this. If we do 2 times the net work, that'd be 4640. And I'm just going to approximate that. Dog is barking. Okay, so a joule is a kilogram meter squared per second squared. Then if we divide by the mass in kilograms, we'll get meters squared per second squared. And then we take the square root, that'll be meters per second. So I'm going to write this. That's around 1. And then, so if we take the square root, this number is just about 1. So the square root's going to be around 1. And then square root of 100 is 10. So it's going to be around 10 or 11 meters per second. I'll just write down 10. It probably rounds off that way. It wouldn't be, maybe 11, but somewhere around that range. Okay, so going to erase this one. Okay, so a mass moves from point A to point B. So in our coordinate system, let's say X and Y are measured in meters. So we start out at point A, which is 2, 1. And it's going to end up at 6, 5. So, say around there. So it's going from here to here. Okay, so a mass moves from point A at location 2, 1, measured in meters, to point B at 6, 5. It's acted on by a constant conservative force so the components are 3 newtons and 2 newtons. So 3 in the X, 2 in the Y. And we want to know the work done by the force. Now, there's different ways that you could do this. We're going to do it the easy way. And because we notice if we look at this displacement, we can make a triangle here. It started at 2 and it ended at 6. So in the X direction, the displacement was 4 meters. And in the y direction, we started at 1 and ended at 5. So it goes up 4 meters. So it's going on a 45-degree angle with respect to the x-axis. The force is not in that same, along that line. It's a more shallow angle. So like the force is something like this. We go over 3 and up 2. So a direct way to do this would be to find this angle between the force and the displacement. I'm going to use delta x as a vector for the displacement. That'd be a direct way to do it. I don't want to do it that way though, because then we could just use our, we could break the force into components or something like that. But I want to do this in a simpler way. And the key here, it says that this force is conservative. And so the actual displacement, say, is on that line from point A to point B. But because the force is conservative, when we calculate the work, we can pick any path we want connecting points A and B. So let's take this path. Let's say we move A horizontally, and then we'll move it up vertically. And again, we can be certain that the work done is the same along, this direct path or this other path because it's a conservative force. So when we go across this first path, we have a force that's in this direction. We only want the component of the force in the direction it's moving, which would be 3 newtons. So let's call this W1. The work along path 1, we'd have 3 newtons times 4 meters. So that would be 12 joules. A newton times a meter is a joule. And then when we go on this vertical path, we know sorry, I wrote that wrong. We know the force has x and y components. That x component doesn't do work on this path because it's in the y direction. So only the y component. So let's call this W2. So path 2, that's that vertical path. We'd have 2 newtons times 4 meters, which would be 8 joules. So the total work would be 20 joules. So this problem could be fairly challenging if you want to just go straight for the definition. Not that unreasonable because we know the path of the displacement makes an angle of 45. We could take an inverse tangent of 2/3 to get the angle, to get this angle, and then subtract that from 45 to find the angle between the force and the displacement, and then take the cosine of that and multiply by the distance from A to B along that straight line path. This way is a bit easier though. And so, and we can be sure we'll get the same answer because it's a conservative force. So no reason to do more work than necessary. So let's just leave it at that. Okay, so let's move on to problem 4. So a 57-kilogram woman runs up a flight of stairs, having a rise of 4.5 meters. So here's the stairs. We're not really told how steep they are. But the rise, a vertical change of 4.5 meters. And she does that in 3.5 seconds. So what average power must she supply? So she's going up the stairs, and again, we want to calculate, she has to overcome gravity. And so, gravity is going to do work. And again, if we look at her displacement, along this diagonal, which we can't really do anyways because we weren't given the slope of the stairs, we weren't given the horizontal distance, but we could calculate the work along that path if we knew how steep it was. But again, gravity is a conservative force. So we can just calculate the work done by gravity as she goes across, which would be 0, and then vertically upwards. So the work done by gravity would be minus mgh, where h is 4.5 meters. And so the work that the runner must do would be opposite that. She has to overcome gravity. And powers work over time. So the work she has to do is mgh. Let's assume she's running up at a constant speed. So this would be like the minimum power. If she exerted more power, she would accelerate on the way up and be going faster. And then let's divide by delta t, which was the time it took her to do it, 3.5 seconds. That's m over delta t, and then 9.8 meters per second squared, and 4.5 meters. Now this will give us watts. We have kilogram times a meter over a second squared. If we just look at these three, kilogram meter over a second squared is a Newton, and then times a meter gives us a joule, divide by a second, we'll get a watt. So, let's see. I'm just going to approximate this. You shouldn't have any trouble getting the actual number. Just 57 times 9.8 times 4.5 divided by 3.5. See if I can approximate this though. This will be around 570. And then 4.5 over 3.5. That's around, say, 1.3. So I'm going to guess it's around 740 watts. So a bit of an approximation. So I don't have a calculator. And, but yeah, it should be fairly close to that. All right. So let's look at number 5. A comet, I'm going to write this down. So the mass of the comet is 8.38 times 10 to the 11 kilograms. And it's moving relative to the Earth at 30 kilometers per second. That would be 30 times 10 to the third meters per second. And we want to know the kinetic energy of this comet. So let's just start out. We have 1/2 times the mass. So actually, this would be 4.19 if we just do m over 2 times 10 to the 11. So m over 2. And then velocity squared, that'd be 9 times 10 to the 8th power. Meters squared per second squared. So I'm writing, 30 times 10 to the third. That's like 3 times 10 to the fourth. So if you square it, 3 squared is 9, 10 to the fourth squared is 10 to the 8th. So we're going to have about 4.19 times 9. Let me just, 81. So it's going to be around 37.7 times 10 to the 19th. And that would be joules, kilogram meter squared per second squared. So this would be around, the kinetic energy would be around 3.77 times 10 to the 20th joules. And now they want us to express this in terms of megatons of TNT. So TNT, of course, very explosive. A megaton, that would be 1 million tons of TNT. So a huge amount there. And 1 megaton of TNT would release 4.2 times 10 to the 15th joules. So let's say let's just call it MT for megaton. That'd be divided by 4.2 times 10 to the 15th power joules. So this is going to give us a very large number. It started as a very large number. It's still going to be pretty big, but smaller in this unit. So let's say 3.8 over 4.2. Let's just say it's around 0.9. Let's see. Maybe that's not. Yeah, 3.8 times 9. Actually, I should do. I'm doing this backwards. Sorry, just checking. Trying to get a reasonable number. Oh, actually, that's very close. 0.9. Okay, so we can say 9 or 0.9 times 10 to the 5th power megatons. Or 9 times 10 to the 4th megatons of TNT. So, yeah, we don't want to get hit by a comet like that. Moving 30 kilometers, very massive object, moving 30 kilometers a second. Yeah, it'd be equivalent to like 90 billion tons of TNT. So, yeah, that's hard to even imagine. All right. So, going to move on to the next one. Halfway through. Okay, so problem 6, we have a thin rod. So, yeah, it says its weight is negligible. Now, later on, we'll learn how we can take the weight into account if it's not, but for now, we can't really deal with that yet. So, we'll just say the mass is negligible. And it's pivoted, so, you know, you could spin it around in a circle if you like. There's a lead ball at the other end with a mass m. And we're going to pull it through an angle and release it. So this angle that we're pulling it through is 35 degrees. So it's free to spin. We pull it through an angle of 35 degrees and release it. And how fast is it moving? So it's going to swing down to this point here. That's where it's moving fastest. It's going to be speeding up all the way down, and then it'll go up, but it'll be slowing back down on the way back up. So we're going to use conservation of energy to figure out how fast it's going. So here, let's do this. Let's say it starts at point A, and it's going to swing through to point B. And so we can say the energy at point A is equal to the energy at point B. And we're going to assume that mechanical energy is conserved here. Now, in reality, there could be friction, but let's just ignore that. So, we have gravitational potential energy. Let's set the lowest point on, the lowest point it's going to swing through. Let's pick that as our reference level and say gravity is 0 at that point. And so initially, the ball is a certain height h above the ground. So the initial energy is mgh. And when it swings through to point B, it has no potential energy, but now it has kinetic energy. And notice, I wrote down the angle. I'm also going to write down the length of the bar, which is 2.13 meters. And we were given the mass, I think, or maybe we weren't, but doesn't matter. We don't care. That cancels out. So we can say that V squared is 2GH. Now the problem is we don't know what H is. We have to figure that out. And so what I'm going to do is draw a horizontal line here. So now we have this triangle. And we can say this side of the triangle is L cosine theta. Let's calculate that. So L cosine of 30 degrees, that's one of those special angles, that's around 0.87. We should be a little bit less than that. I'm going to say 0.85 for cosine of theta. So 2.13 times 0.85. So this length is about 1.81 meters from here to here. And then, when the rod swings through the lowest point, the rod is going to be hanging vertically. So this distance from here to here would be the length, 2.13 meters. And so if we subtract that, then we'll get our height. So if we subtract 1.81, that'll give us the height. So it starts out about 32 centimeters above the lowest point of its swing. And so now we can just plug things in. We have 2 times 9.8. That'd be 19.6 meters per second squared. And then times 0.32 meters. So our units are going to be meters squared per second squared, and then we'll take the square root. 0.32 is roughly a third. So if we do 19.6 divided by 3, so like around 6.5. So V squared is going to be around 6.5 meters squared per second squared. And then we take the square root of that. I think that's around 2.5 or 2.6. I'm going to say around 2.5 meters per second. Again, not using a calculator. The numbers I'm getting could be a little bit off. Hopefully they're not too far off. Okay, so let's move on to the next one. Let's erase this. All right, so one end of a vertical spring is fastened to the ceiling. Then we attach a weight to it and slowly lower it to equilibrium. And then show that the loss of gravitational potential energy of the weight equals 1/2 the gain in the spring's potential energy. So we have a spring here. Now we don't know much about this spring. Let's just say it has a force constant K. And so this is the initial here. And then we're going to attach a mass to it, and we're going to slowly lower it down. So if you just attach a mass and release it, it's going to drop down. But here we're slowly lowering it down to its equilibrium position. And that will occur when the upward force of the spring is equal to the force of gravity. Again, we're not given any numbers here. So let's calculate the loss of gravitational potential energy. So the spring force, let's call that K times Y. So Y is the displacement from equilibrium. So we can solve for Y. Let's set them equal to each other because the net force isn't zero. It's in equilibrium. So Y is equal to mg over K. And so the change in potential energy, the loss of gravitational potential energy. Now, they're asking for a loss. So this is a change in gravitational potential energy. Let's just look at the magnitude. That would be mgy. So y is its, it started out here. Y would be the stretch from that length. And so that's the distance this mass fell. So it's losing potential energy as it does so. And so, that's mgy. If we plug in, y is equal to mg over k, we get m squared g squared over k. So that's the loss of gravitational potential energy. I want to check the units here real quickly. We know that mg is a force. So here we have Newton squared divided by k, which is newtons per meter. So yeah, this will give us a Newton times a meter, which is a joule. So unit-wise, this checks out. That's the loss of gravitational potential energy. Now, let me read the question again. Show that the loss of gravitational potential energy is 1/2 the gain in the spring potential energy. So the spring potential energy is 1/2 kx squared. So let's plug in the numbers here. Or let's call it y, because that's what we've been calling it. So let's see, we'd have k over 2, and then m squared g squared divided by k squared. So one of the k's cancel out. So we'll have 1/2 m squared g squared over k. So 1/2. So again, we're showing exactly what they wanted us to do. The spring potential energy changed by 1/2 m squared g squared over k. So 1/2 the change in gravitational potential energy. And then the question says, why are these two quantities not equal? And so we're looking at, in a sense, there's no kinetic energy involved. We lower it slowly. And mechanical energy does not appear to be conserved in this case. It lost this much energy, but it has this much stored, but it has less stored energy than it lost. And we can't really expect the energy, or we can't expect mechanical energy to be conserved here, because as we were lowering it, we had this other force involved that we didn't write down, but we have gravity downwards, and so we had that spring force, but we also had an applied force. Like say you're holding the mass as it's falling. So as it's falling, you're exerting an upward force, and you're doing negative work on this object. So the total work done on this object, by that applied force would be negative. And so we were not taking that into account, just looking at the potential energy of gravity and the spring. So we shouldn't expect these to be equal. That applied force, if we didn't do that, so if we just had this applied force, if we remove that and just attach the mass and released it, then it would bounce around and it would have kinetic energy as well. So, yeah, that one, that's just one of those problems, kind of abstract. There's no numbers. You're not calculating anything numerically. And just really thinking about conservation of energy. Like what's going on as this mass is being lowered. All right. So 3 left. Problem 8. Let me erase this one. Okay, so we've got this track. That looks like this. And let me read. So that we're given a radius r. And from the ground, this distance is h. So you can picture, like, maybe you've seen like a toy where you've got this track and you can put a car on it. And you can build things like this where it'll roll down the track, and then if it's going fast enough, it'll loop around the track without falling off. So, well, yeah, let's read the problem. So it says a small block of mass m slides along the frictionless loop-the-loop track. What minimum height h must the block be released so that it makes it around the loop? So we have to be able to make it all the way around the loop. So this one is actually kind of a tricky question. Because if it's not going to make it around, the one point that you're going to have an issue with, or the area, it's going to be fine here, and then it's slowing down. How do we know if it's going to be going fast enough? If it stops somewhere, it's not going to reach the top. So let's label this point A and this point B. And we want to make sure we have enough speed to make it around, but we can look at this in terms of energy. So at point A, the energy we have is mgh. And there's no friction, not the most realistic thing. But if we look at point B, we have both potential and kinetic energy. The potential energy is mg times 2r. Because, from the ground, we're saying that ground is our reference level, where potential energy is 0. And so at point B, its height above the ground is 2r. And then we'd have the kinetic energy. I'll just write kinetic energy at B, because I'm out of room to write any more. And so, basically, we want to solve for h. But in order to be able to move around this circle, if we look at point B, let's say here's the mass at point B, the only force, well, there could be 2 forces acting on this mass at point B. There's going to be gravity pulling down. There could also be a normal force downwards from the track pushing down on the car, or this mass. So you can imagine if this mass is moving very fast, as it wants to keep going up. And gravity is pulling it down, but if gravity is not enough, the track has to push it down to keep it moving in a circle. Like if the track wasn't there, if it's going fast, it wants to keep flying upwards. So the track generally will push downwards on the mass. But at the minimum speed, the faster it's going, the more the track is going to have to push down. And so if we kind of just lower the speed, like say we keep releasing it from lower heights so that it's getting slower and slower as it approaches point B, at one speed, the normal force would disappear at point B. So it keeps getting smaller. At some point, it's going to disappear. And then if you're going any slower than that, you just won't make it around the track at all. So we can, to find like the minimum speed, we can say that the normal force equals 0 at point B. And then if it's going faster, you know, the normal force will push downwards, but let's just say we're going at the minimum speed. And so gravity is downward and it's moving in a circle. So we can say that, you know, just force equals mass times acceleration, where we know for circular motion that inward acceleration is v squared over r. And we can solve for v squared. It's capital R to keep it consistent with the picture. So v squared would be g times capital R. Those masses cancel out. So let's look at this equation again. Here, I'll write it here so I have room. We have mg times capital H equals mg times 2r, and kinetic energy is 1/2 m times v squared, which is gr. So a couple interesting things here. One, we can cancel out the mass. So it doesn't matter what the mass is. You'd always have to release it from that same height in order to give it enough speed to make it around the loop. Interestingly enough, gravity cancels out as well. We can divide by g. And so what that means is we could find that height, and then we could go to the moon and do this, and it would work just the same there. So gravity is not a factor. So if we just divide everything by mg, we have h equals 2r. So yeah, mg cancels out, plus r over 2. So we can write 2r as 4r over 2, and then plus r over 2. So the height only depends on the radius. It's 5r over 2. So yeah, mass is irrelevant, and even gravity. Okay, so again, kind of a tricky problem. Two more to go. It's when is today? Well, it's a couple days to July 4th, so I don't know if you can hear fireworks in the background. Nothing official, just people lighting them off, and dog is barking. Right. All right, two more. So here, when a space shuttle with a mass of 79,000 kilograms, so rather large object here. So it returns to Earth from orbit. So it enters a speed moving 8,000 meters per second. It enters the atmosphere going that fast. And it's going to slow down. You know, when it lands, it'll be moving 100 meters per second. So that's still pretty fast, 100 meters per second. You know, it's over 200 miles an hour, I think. But very significant change in velocity. And what is the kinetic energy as it enters the atmosphere and then at touchdown? So let's calculate the energy when it enters the atmosphere. So K initial, we have 1/2 times the mass, which is 79,000. And then the velocity squared, I'm just going to square it. 8 squared is 64. And so we have 8 times 1,000, so that'd be 10 to the third. When we square it, we get 10 to the 6. So unit-wise, kilogram meter squared per second squared is a joule. So we have 79,000 times 64 over. Here, let's clean this up a little bit. I'm going to write 79 as 79 times 10 to the third. I'll add that later. 64 over 2 is 32. And then we have times 10 to the 9th power joules. So we have 79 times 10 to the third, and then times 10 to the 6 is 10 to the 9. 64 over 2 is 32. So let's see, 79 times 32. So let's say 2.53 times 10 to the 12th joules. So 2.5 trillion joules of energy when it enters the atmosphere. It's a rather large number. And, that energy has to go somewhere. So, when it touches down, obviously it's going to have a lot less energy. And, where does all that energy go? Well, it's mostly dissipated in heat. If you've ever seen the shuttle, it actually glows from the heat. It's very dangerous for something to come in from orbit. This is one of the reasons why. I guess if you approach it the wrong angle, you can kind of skip off the atmosphere too. But even if you get it right, you have to get rid of all this energy. And so they're very heat-resistant tiles. But they go through a lot. But anyways, let's find the kinetic energy at touchdown since we've been asked to. So let's see, 79,000 kilograms. And then 100 meters per second, when we square that, that'd be 10 to the 4th. So if we do this again, we'll have 79 over 2. And then times 10 to the 7th power joules. So here we have 79 times 10 to the 3 times 10 to the 4. That'd be 10 to the 7th. And divided by 2. So 79 over 2. That's 39.5. Let's just round off. Say 4 times 10 to the 8th power. So again, basically this is essentially nothing compared to what we started with. If we wrote this as 10 to the 12th power to get the exponents the same, it'd be like 0.0004. It'd be somewhere over here where, subtracting these values, we'd essentially get that unless we had more significant figures. So essentially all this energy it had is converted into heat. Which is one thing that makes rockets and re-entry so dangerous. Okay. So we've got one more problem to do. And this is something we haven't talked about yet in class. What do we do if energy is not conserved? A lot of our problems are about conservation of energy. But this last problem, we have a swimmer jumping from a diving board. So let's say here's water, the surface of the water. And the swimmer's on a diving board, going to, dive in, sink a certain distance, and then come to rest. And so obviously when you hit the water, water is going to have significant a resistive force. If you go into water at high speed, you'll come to rest fairly quickly. And that's basically what we want to find on some level. So let me read this. Swimmer with a mass of 52 kilograms jumps from a diving board a height 3.2 meters above the pool. Let's call that H. So it's 3.2 meters. And then the swimmer will sink to a depth of 1.8 meters. So let's call that D. And the question is, what was the average force that the water exerted on the swimmer during the descent? So here's what we're going to do. Let's start out and look at gravitational potential energy. Let's pick our reference level to be the lowest point. So, 1.8 meters below the ground. And so we can see, if we just compare, say point A is when the swimmer jumps, and point B, energy is clearly not conserved in this case. The swimmer has potential energy here, and that's it, just gravitational potential energy here. But at this bottom point, the lowest point that she sinks to, she'll come to rest here. And so no kinetic energy and no potential either. And so we have to learn how to deal with cases where energy disappears or is carried away from our system. And the idea is to look at this kind of like an accounting problem. Energy never disappears. You just have to keep track of where it's going. And so we can kind of, in general, for when mechanical energy is conserved, we can say like energy at A equals energy at B. Just take any 2 points. If energy is conserved, it has to be equal there. But more generally, if energy is not conserved, we can just simply say this. We can add another term. So, like for example, say you start with 1,000. Different example. Just want to make up some numbers. So let's say you have 1,000 joules of energy at the start. So we're going to place an object on a ramp and let it slide down to the bottom. So we say it starts out with 1,000 joules of energy, and let's say when it reaches the bottom, it only has 700 joules. And we're talking about mechanical energy. And so where did that missing energy go? Or how much energy was removed from the system? Well, it'd be 300 joules. So we could say the energy lost in this example is just 300 joules. And so, figuring out how much energy is lost, that could be a difficult thing. Like in this problem, if I was giving you a problem like this, I would just tell you that 300 joules was lost on the way down the ramp, and then you can figure out if you know how much you started with. And if I told you lost 300 joules, then you know you have 700 joules of mechanical energy at the bottom. So even if energy is not conserved, we can use these concepts to, these energy concepts to still, work with. But the, finding out, calculating the amount of energy lost can be difficult in some cases. But actually here, that's not going to be all that difficult, because the energy at A is mgh. Actually, let me be a little more clear. H would be our height above the reference level. So that would be H plus D. So that's how much energy the swimmer has at point A. And the energy at point B is 0, the mechanical energy. There's no potential energy at point B, and the swimmer comes to a rest. And so the energy lost would just be whatever the swimmer started with. Let's calculate that. So the energy lost, that would be mg, so 52 kilograms, times 9.8 meters per second squared, and then h plus d, that's just 5 meters, so that's convenient. So we can calculate how much energy the swimmer started with. That's also the amount of energy removed. So let's do this. 52 times 5 is 260. So So this would be around 2,550 joules. That's how much the swimmer started with, and all of that was dissipated by the time she reached point B. Okay. So now the question, though, is what was the average force that the water exerted on the swimmer during this descent? And so we can say the total work being done by this force, by the water, would just be this average force times d. So it'd be the, d is the distance that force was applied. And so the average force, we'd have about 2,550 joules. I'm going to write that as a kilogram meter squared per second squared. And then we divide by 1.8 meters. So that cancels out. So we have kilogram meter per second squared. This would give us a force in newtons. And I'm just going to kind of approximate this. I'm going to say like 1,300 newtons. And actually check that. See if it's close. It should be a little higher. Actually, that's pretty close. Yeah, around 1,400 newtons would be the average force. Now, I just made up this problem without checking the numbers. That's actually a pretty significant force. So maybe she's like belly flopped, and probably not a good idea. But yeah, that's how you can deal with problems when energy is not conserved. Okay, so I'll stop it here, and if you have any questions on any of these, we can talk about them during class.